Hello, everyone. My name is Dawn Oh, and today I'm going to talk about dynamics and physics, but in common sense, we're going to take a look at what force is and the relationship between motion and forces. Okay, before we start, as you can see on the slide, there is a box on top of a table. The box is not moving. In other words, it is at rest. Even if we don't know what exactly force is, you might have heard of something called gravitational force. The Earth is pulling us downward, and that becomes the reason why we cannot fly on Earth. So there must be at least a gravitational force acting down to the subject, but we said that the box is at rest. Even if the force exists, the subject is not moving. After this lecture, you will be able to explain what makes the box stay at rest. So first, force from the common word gravitational force is what changes the state of motion. It is an interaction between two objects that requires an agent to act forces on an object. It is a vector quantity, which means it has a magnitude and direction. So in order to find a net force, which means the sum of all forces acting on the object, we need to do the vector addition and subtraction. If you do not know what a vector is and don't know how to calculate vector addition or subtraction, I recommend you to learn that first and then come back to this lecture. We have another video from another KGSEA member tutoring about vectors and scalars, so why don't you go and watch that first? And if you decide to stay in this video, I will assume that you're familiar with vectors. And coming back to force, think of net force as the vector that decides how far the object goes in which direction. Like you decide how far the ball would go in which direction before you kick one. You are the agent in that case giving the force to the ball. And there are two types of forces, contact force and field force. Contact force is a self-explanatory that agent and object needs to contact each other, and field force does not. Gravitational force is an example of the field force. To understand forces better, it is necessary to know Newton's 3 laws of motion. The first law is also known as the law of inertia. When the net force acting on the object equals 0, the object continues its state of motion, moving with constant velocity and 0 acceleration. So in other words, an object that is at rest will remain at rest, and an object that is moving will continue to move with constant velocity and 0 acceleration. The second law is most commonly known one, which is F equals ma. The force is directly proportional to the acceleration of an object and inversely proportional to its mass. So if there exists a net external force acting on the object, it accelerates and the direction of the object is the same as the direction of the net force. The third and last law is the law of action-reaction pairs. I have told you that force is an interaction between two objects. So if object A and B interact, the force of A on B has an equal magnitude but opposite direction of force B on A. So let's take a look at common types of forces around us. The first is a gravitational force, the most common force. As I said before, it is the force exerted by the Earth on an object directly toward the center of the Earth. When an object is freely falling, like when we drop a pencil from the table, recalling F equals ma, the value of acceleration is fixed to g, which has a value of 9.8 meters per second square. Next is a normal force. This is a force to support an object against gravity, and the direction of the force is always perpendicular to the surface that an object contacts. Since it is a contact force, when the object is off the surface, the normal force is 0. The following force is the friction force. It is always parallel to the contacting surfaces, opposing the sliding motion. There are two types of friction forces, kinetic friction and static friction. Kinetic friction acts when the object slides over a surface, and static friction acts when there is no relative motion. So when we're trying to move an object on the surface parallel to the surface, the value of static friction is the minimum force necessary to move an object. Unless we give that minimum force to move an object, the static friction would be the same magnitude as our given force according to Newton's third law of motion. The last force we're going to talk about is a spring force. When a spring is stretched or compressed from its unstressed position by a displacement x, the force it exerts is found to be negative kx, which is known to be Hooke's law. So when the spring is in its unstressed position, which is in stable equilibrium, x equals 0 so that the next net force becomes 0. But when it is stretched or compressed, the spring has the property to go back to its equilibrium position. So since the displacement has the opposite direction from the spring force, there is a negative sign in front of K, which is a spring constant. There are some other forces such as drag, tension, and thrust force, but we're not going to dip into these forces, but I will briefly explain them to you. Drag force is what we call air resistance. Tension is a force from a string exerting when it pulls an object. Note that it is always pulling away from the object, not pushing. Thrust force is a mechanical force generated by the engines to move the aircraft through the air. Drag and thrust force might seem to be field forces, but all three are contact forces. So that was all for the introduction of the common types of forces. But to easily solve questions, especially to answer our question, why the box on top of a table is not moving, we need to get familiar with drawing free body diagrams. A diagram showing the chosen mass point, which is an object, with vectors drawn to show the magnitudes and directions of all forces applied to that object. It is called free body diagram because the object is free of its surrounding, which means we are not drawing surroundings in the diagram. Let's dive into an example right away. With the box problem that we have to answer, first, we have the gravitational force acting down to the object. And since the box is on top of the table, there exists a normal force perpendicular to the surface. The box is at rest, which means the net force applied to the box equals 0. So the gravitational force and normal force need to cancel each other. The magnitude of the normal force to be also mg. So that's pretty simple, right? And unlike the box problem, when we have an inclined surface, it is important to divide the force into components when drawing free body diagrams. There are a total of 3 forces: gravitational force, normal force, and friction force acting on the object. Since the object is at rest, the friction force is specified to static friction and net force equals 0, which means all forces cancel one another. To see that visually, we divide gravitational force into 2 components, and one would be mg cosine theta and the other would be mg sine theta. Then we can see that the magnitude of normal force equals mg cosine theta and static friction force equals to mg sine theta to make net force 0. To sum up what we learned, let's try to solve some practice problems together. This problem is from AP Physics C Mechanics practice test. It says a box is on an inclined angle theta above the horizontal. The box may be subject to the following forces: frictional, gravitational, tension from a string connected to it, and normal. In the following 3 diagrams for the box, the length of the vectors are proportional to the magnitude of the forces. Following that description, question 10 says, which of the following best represents free body diagram for the box if it is deaccelerating as it goes up the incline? Since the box is decelerating as it goes up the incline, there should be a frictional force acting that is parallel to the surface, opposite to the box's motion. A cannot be the answer because the gravitational force has to point directly toward the center of the Earth. Then we're left with choice D. Question 11 says, which of the following best represents the free body diagram of the box if it is moving at a constant velocity down the ramp? The constant velocity means there is no acceleration to change velocity, which means net force equals 0, according to Newton's first law of motion. All forces need to cancel one another, which we are left with choice C. Question 12 says, which of the following best represents the free body diagram for the box if its speed is increasing as it moves down the incline? Since the speed is increasing, there exists acceleration to change velocity, meaning there exists net force. We said that figure C is a free diagram of a box at rest from the previous question. Then to make net force not equal to 0, all we have to do is add one more force acting on the box, which is choice E. And that is the end of this lecture. Problems about inclined planes might be a bit complicated, so if you cannot understand them at once, try to solve some problems without those surfaces and also stop the video when rewatching it to make them yours. And don't forget to keep Newton's 3 laws of motion in mind so that you can recall anytime. I hope you enjoyed it and thank you.